Okay, hello everyone. I guess we are ready to start more or less. Okay, so hello everyone. My name is Dimitris, and this is Deep Learning with Python, the second half of the 11th chapter. So the previous week we attended the first half, and now we will see the rest, which is again deep learning for text, but this time we are going to introduce the notion of transformer, what is the transformer architecture, and also the sequence to sequence learning, which of course is very useful in case we want to do something like text translation or this kind of tasks. So let's see in more detail. First of all, a few words regarding the transformer architecture. It was introduced in the beginning of 2017, and it was a new model architecture, completely different than things that existed already. The name of the architecture was the transformer, and it was introduced in the Attention is All You Need paper, very influential paper, not only for natural language processing, but also afterwards for computer vision too. So the idea is that a simple mechanism called neural attention could be used in order to build very powerful sequence models without having to have any layers of recurrent layers or any convolution layers in case we have computer vision. Let's see in more detail what is this idea. So the main idea, the key point idea is that not all the input information is useful for the model in order to perform a specific task. So there are some specific details or information from the input that the model should pay more attention, and some other features that it should pay less attention. And we have already seen something similar, actually. I mean, the whole idea of max pooling, for example, is that it gets the maximum activation for a specific feature. So it's something like a binary way of all or nothing form of attention. Also, we have already talked about the TF-IDF normalization way, which more or less assigns more important scores to the tokens that are more relevant, and while the irrelevant tokens, they are faded out. So the idea is that it's more of a continuous version instead of the max pooling, which is a very binary. So let's see an example of what it would look like, for example, for an image. So at the top, we have the original representation. We have an image, and then we want to get only the information from the image that is important for the task. So the whole idea is that we have some mechanism, the attention mechanism, which will assign some attention scores on the image. And based on these scores, we will combine with the original input to have the new kind of representation. Now, let's see how this works. So let's understand the self-attention mechanism. The idea is that this mechanism can be used in order to make features that are context aware. So the idea is to produce some vector space which captures the shape of the semantic relationships between the different words. Up to this point, we have already seen, for example, the word appendix, which creates some vector space where each word has a fixed position. Of course, it has it captures the notion, the meaning of the word, but the idea here with word embeddings is that it's only a very specific point in the space. But the meaning of the word is usually context specific. So for example, we have the word date. The meaning of the word date in the sentence, for example, I have a date with that girl tomorrow evening, and the word date in the sentence, I don't know, what is a date today, is completely different. So we have to know what is the context of the sentence in order to understand the meaning of the word. And this is more or less the idea of the self-attention mechanism. So a smart embedding space would provide a different vector representation for the word depending on the other words surrounding it. So the purpose of the self-attention is to modulate the representation of a token by using the representations of the related tokens in the sequence. Now let's see how this works. So the idea is quite simple. We have an input sentence, an input sequence like this, for example. By the way, all this can be applied not only for words, but now we will see the example with words where we have the word embeddings. So for each token, for example, the words, we have the train left the station on time. And we want to get a new representation for the word station that is related to the sentence. So a train station in this case. So we take the embeddings that we already have for each word, and then we get the pair, each pair of the sentence. So we have the word there with the with train, etc. And then we apply something very simple, which is the dot product. So the dot product gives us some kind of relevancy score. So how relevant are the two embeddings of the two words? And here you can see, of course, the diagonal is 1 because it's totally relevant. But you can see, for example, for the word station, we have, if we compare it to the word the, we have a quite low relevancy score. But if we compare it to the embedding of the word train, we have quite high. Also with left, etc. So the idea is that we take these dot products and we have one number, one score per word for each one of these words, for example, here with the word station. And then we apply some processing. For example, in this case, we apply softmax. We multiply with a specific factor which is 1 divided by the square root of this. But after this, we have the weights. So we have one weight for each word. And what we do is that we take the weighted sum. So we multiply the embedding of each one of these words by the scores, and then we just take the sum. And this sum will be the context-aware vector. So this simple idea is quite powerful because it gives us the whole notion of the context around each word. Now let's see what this would look like in simple Python code. So let's define the self-attention, and this takes the input sequence, so all these tokens. We create the output, so the new representations, and then we pivot for each vector, so for each embedding, for each vector of it, for each token. So we take this, and we first of all we create the scores that we have to multiply afterwards, and then we take each one of the existing vectors. And we take the dot product of the pivot vector with each one of these vectors. And we assign the value to the scores. And then we just apply this multiplication and this softmax on the scores. And after we have these scores, we just take each one of these scores and we multiply with the vector that corresponds to this score. So we have a vector and we have one number. So we multiply them and we get the sum. So when we have the sum, we just assign it to the outputs. And this way we get the output representations based on this attention mechanism. So now let's see how we can use this simple idea to make something quite powerful. What we saw before, first of all, what we already saw is includes for loops. Of course, it's not optimized. So there is the vectorized implementation of self-attention mechanism of this mechanism in Keras. And in order to use this, we will have to import the multi-head attention layer. So let's see how this works. First of all, we have to define the number of heads. We don't yet know what heads is. We will explain it. And the number of dimensions. So this will be just the output vector. What is the dimensionality of the output vector? And then we create this multi-head attention layer where we have the number of heads, we have the what is the embedding dimension, and then the output, like we had before, will be this layer where we import 3 times the inputs. Okay, so the inputs is just the sentence. Now, why 3 times? So usually you would expect that we will input this sentence, these tokens, only once. But here you can see that we use it 3 times. So the idea behind this is that, of course, if we have one sentence and we want to classify the sentence, we don't have 3 sequences, we have 1 sequence. This is why we input the same one 3 times. But there are cases where we don't have only one sequence. For example, if we want to make to have a task of translation, we have 2 sequences. So the idea is that we will have 1 time 1 sequence and 2 times the other sequence here. And there are even examples where we will have 3 different sequences. So let's see what exactly is each one of these inputs. Here's the main idea is that the outputs will be these inputs, C, times the pairwise score between this and this, A and B. Now, what is A, B, and C in this case? So this sentence explains what we do. So for each token in input A, we compute how much the token is related to every token from input B. And then we use these scores to weight the sum of the tokens of input C. This is an example of how we can see these 3 different inputs. So let's say we have a search engine where we search for photos, so for images. Now, one sequence, one input will be the query. For example, we search for the dog on the beach, okay? Now we have the images, which is another sequence, and we try to find the relevance. So in this case, we have, let's say, these images. And then, since we cannot compare the query with the values directly, we use the keys. So each one of these parts of the sequence has a specific representation, the keys, for example, the keywords. And what we can do is compare each word of this with each word of this in order to find the relevance of this query to these values through the keys. So this is why we have 3 inputs, 3 times the input. So if we have, again, classification, it's 3 times the same. If we have a translation, it's 1 and 2. And if we have something more complicated, it could be 3. So in this case, for example, it would be, the source would be, if we have translations, how is the weather today? And the target would be και τι αθε oi. And the query will be the target, and the key and the values will be the source, so the English words. Now, this explains why we have 3 times the input, but why we have the number of heads? What was this number of heads? So the idea is quite simple. Multihead, which is the name of the layer, means that the output space of the self-attention layer gets factored in a set of independent subspaces learned separately. So we have the initial key, query, and value, so this triplet, and send them through 3 different sets of dense projections. And this results to 3 separate vectors. So they are learned separately, so they are independent with each other. And each vector is processed then, after this, with the neural attention. And then we have the 3 outputs that are concatenated in order to get them back to to produce the output sequence. So this is more or less the idea that we have already seen when we talked about the depth-wise separable convolution networks. So in these layers, we have each one of the feature maps, that is the output of the previous layer, to be treated separately, independent to each other. So it's not like the convolution, for example, where we take all of them and we treat them all together. We break them. And there are some other techniques where we have some grouped convolutions. So we take, for example, the 64 feature maps and we break them to groups, let's say 4 groups. And each group has specific feature maps that we treat as one category. And we have the convolution on all of these. Similar idea is the multi-head. So we have the same input processed with different heads that they learn different representations, and then we concatenate this knowledge. So let's see how this would work. So the presence of the learnable dense projection, we will see the architecture later on, enables the layer to learn something as opposed to being a purely stateless transformation. The idea here is that the attention mechanism that we saw before, where we have the dot product and the scores and etc., it doesn't learn anything. So it's just an operation. It doesn't have any weights, it doesn't have any internal states. So in order to learn something, you use these learnable dense projections. And as we said before, the independent heads help to for the layer to learn independent groups of features for each token. So this is more or less how it works. We have, again, the three sequences, which can be the same, the key, the value, and the query. And for each head, so this is one attention head, this is another independent, we feed them each one of these sequences to a separate dense layer. So here is the learning part of the head. After we have the output of this dense layer, we input this to the attention mechanism, similar to what we saw before. And then after we have all this, we just concatenate them. We merge the results to this output. And this is more or less what is the transformer encoder idea. So let's talk in more detail regarding the transformer encoder. The idea is that since we have this, we saw before that inside the head, we have these dense layers that learn some features regarding the task. And since we have this and they learn something, the idea is why not use also dense layers after the output of the multi-head attention. So the idea is that we take whatever is the output and we pass it through another dense projection with two dense layers so that we can learn even more information. And also we add some standard techniques like the residual connection here, for example, or here, which is quite useful and helps us get deeper to add more of these blocks. And also we can add the normalization, so layer normalization, which is better for the gradients flow. So this is just things that we use in order to get the training run smoother. Be careful here, it's layer normalization, it's not batch normalization. And this is because layer normalization works better for sequences instead of, for example, for images where we have something like batch normalization. So this was the part of the encoder. Again, let's see, because we will actually build this, so try to remember more or less the idea. We have the multi-head. Again, so let's go back. The multi-head was this. We take the inputs, we pass them through dense layer, each one, and then we have the attention layer. And the output is concatenated. Now, let's see the what happens after this multi-head. We take this, we apply the residual connection, layer normalization, and then we keep it for the residual, and we use three dense layers. The output with the residual, we add it, and then again, layer normalization. Quite simple. Now, let's see what else we have. So the idea is that this is the encoder part, and the transformer architecture has the encoder part and the decoder part. Now, the encoder part, that is what we just saw, is actually useful by itself. So, for example, if we want to have some text classification, we can just use the encoder. We don't need any decoder. And the output of the encoder can be passed through, I don't know, a dense layer, and we can classify the output, the sequence, the sentence. So let's see an example. So here we will use the IMDb datasets, the one that we have already seen before. So for each movie, we have a positive or a negative review. It's exactly the same that we used in the last time. And you can see that we have 20,000 data in two classes, positive and negative for training, some 5,000 for validation, and 25,000 for testing. So, and actually, the idea is that what we will see now, the encoder part, is a very generic module. So it can ingest any sequence and it learns how to turn it into a more useful representation, which is what we want. So think of it as an embedding layer. So a glorified embedding layer. It takes some sequences and it produces just a representation. That's all it does. And then we can take the representation to pass it through a classifier or to use it for decoding later on. Now, let's first of all vectorize the data. So this is more or less what we saw last time. So nothing new here. We define how many, the max length for how many tokens we will have for each sentence. and the maximum tokens, which is again how many words will be in the vocabulary. And we just apply what we did before. So we get the integer trained datasets, integer valid, and test. So let's run this one. And now we have the representations with integers, not embedding yet. So let's see what we have here. And for example, we have here we take just around the first sample of the test dataset, and we see that we have 32, which is a batch size, by 600. So one number, which is the index of the word in the vocabulary. And of course, the output will be just 0 or 1, so 32 numbers. So let's continue. The transformer encoder, how we can implement it as a keras layer. So this is more or less what we can do. First of all, this will be an inherit from the layers.layer. So we have already seen this. We have to define the init, we have to define the call, and get config in case we want to load it again. So first of all, we just pass the information we need. We assign them here. We call, of course, the super init for the layer. We assign this information to self in order to use them also for config. And the important thing is here. So we have this multi-head attention, which is the layer that we saw before, where we define how many heads and what is the embedding dim. And then we also have the dense projection, which is a sequential of two dense layers. So we have the intermediate with whatever dense dimension, and the output, which will be the embedding dimension. And of course, we have the two layer normalization layers, and we define them here because they have some learnable parameters. So, and here's the call. Here is what actually happens to the input. So when we have the inputs, first of all, we do this trick, we apply this trick in order to be consumable for the layer, the mask. And then we take the inputs and we pass them to the attention. So in this case, we just have to do it pass them 2 times because it's implied that it will be the same. And for the attention mask, we define this mask. Remember, this is important in order to not pay attention to the rest of the to the zeros that we have in order to have 600 for each one. So we take this attention output from the multi-head. If you remember, we apply the residual connection here with the inputs, and then we apply the normalization. Then we pass the output through the dense projection, and then we take this output and this input, we apply the residual addition, the connection, and again, we pass them through the second layer normalization. So more or less exactly what we saw in the diagram before. And this is get config, nothing new here. So let's see what we can do with this layer. Let's build a model which will have this layer, and more or less the rest will be exactly what we saw before. So same as before, we have the embedding. Now here, instead of some recurrent network layer or bidirectional or whatever we had, here we will have this transformer encoder layer. And then after that, it's again exactly the same. We have the global max pooling, the dropout, and the dense layer because we want again to classify positive or negative. So nothing new here. The only new thing is this one. Let's build the model. And here's the summary. So the idea, again, in order to understand how this works, okay, the first known here will be the batch dimension. So let's say 64 or something. This known will be the how many words we have, for example, 600 in our case. We could have passed it here if we wanted, but we didn't. So the input will be 600 numbers, integers, just the indices of the for the dictionary. And then the output of the embedding will be 600 times 256. And you can see here that the output of this transformer encoder is exactly as the output of the embedding. So we have 600 times 256 again. But now we have this information fused with each other. So we have this self-attention mechanism, and we have this information with the relevance of the context. And after that, it's again the same. So global average, we have just for the whole sentence, one number per feature that we're interested in. So one number per the 256 features, and then we apply the dropout, etc. Let's continue now. So we have the, here we should actually train the model. I have again already trained the model. So let's go directly to the test accuracy. And if you remember from the previous ones, we had, okay, now we have 8.87.7. So this is what we left from the previous time, so from the first part. And the idea from the first part is that we had this one that was actually pretty good, nothing else was that good. And here, although we have this mechanism, this new mechanism, which is really good, we see that it's still not better than the two dense layers. It's pretty annoying. I mean, these are pretty good in comparison even with this. Of course, it can get better if we have something deeper, but still, it's quite annoying. What else can we do? So how can we make this better? And why the basic model is actually better. So the idea is that the current transformer model, what we just saw, is actually not a sequence model. So the attention layer by itself doesn't look at the tokens as sequence. It looks at the tokens as a set, which means that it doesn't matter if we change the order of the tokens, because it's just interested in what is the relation between the tokens. I mean, the vectors of the tokens, not which is first, which is second. So here is a table where we can see this thing. We have the different approaches that we have already seen, the bag of unigraphs, biograms, etc. If there is word order awareness, and if there is context awareness. So of course, bag of unigrams has nothing. Bag of biograms has some, it knows which is the previous and the next word, but of course not context aware. RNN has the word order because it treats the sentence as a sequence, but not context. And then we have the self-attention, what we just implemented, which doesn't have word awareness, but has the context awareness. And now we will see the actual transformer, which has both. So how can we import this information? How can we inject this information regarding the position of the word? So the positional encoding gives the model the access to the order of the word in the sentence, in the sequence. And it adds the word's position to each word embedding. So we have the word embeddings that are the outputs of the embedding layer. And now what we are going to do is to add also an embedding for the position of the word, not only the word itself. So the actual word embeddings will have two components, the word vector, which is what we saw before, just the output of the embedding layer, and the position vector, which will represent the position of the word. And now we will see how we can actually implement this. It's quite different than the original paper, but it's something actually totally valid, and this mechanism is actually used. So the model will learn actually the position embedding vectors the same way that it learns the embedding word indices. Now, let's see how we will implement this. Again, we subclass from the layer, and this is the positional embedding, which outputs both the actual embedding and the positional embedding. Just the inputs here, nothing really different. Here are the layers. So we have the layer, the embedding layer, what we had before. And now we also have a new embedding layer, which will be the positional embeddings. Here we have as input dimension the sequence length, so the 600. This is the input dimension, and the output dimension will be exactly the same as this. For example, it will be 256. And here we have the sequence length, and the input dimension and the output dimension. We just pass them here in order to get the config. So the important thing is these two things. First of all, let's see the call. So for the call, we need the position. So the same way we have the indices, the index of each word in the vocabulary, we want the index of each word in the sentence, the actual position. So we get the length and we create these positions. So it's just a TF range. And then we get the embedded tokens, which will be the output. We pass these numbers, these integers, to the token embedding first. And then we also have the positional embedding. So we pass the positions. So first of all, the inputs to the token embedding and the positions to the positional embedding. And then we have these two and we just add them. And in order to compute the mask, because we need to output the same way that the embedding layer outputs the mask, we want this layer to output the mask. So we want the same mask as the embedding, which means that we take the inputs. If you remember, this is just the integer. So 1, 2, 3, whatever, up to 599 if it's a word, or 0 if it's not a word. So whenever it's 0, we will output 0. Otherwise, we will output 1. And that's all more or less. So not something very complicated here. Just the two embeddings and we add them. Now, let's put it all together and use it in the same example that we saw before. So this is exactly what we had before, with this only change, that instead of having an embedding layer, here we have the position embedding layer. And the output, we just feed it here to the transformer encoder. So let's see how this will roll. And here is exactly the same output shapes as we had before. So this didn't change, we just added something. And here you can see that it's actually quite better. So 88.5, we got 1% just for this, which is pretty good. So it did improve, but again, not as good as the bug of words ones. Now, so the bug of words was actually pretty good, better than the RNN, better than even the transformers. So the question is, what's going on? When should I use a bug of words and when should I use these new techniques? And it's important because actually the bug of words approach is not outdated at all. So we would think that, okay, we have language related tasks. So of course we will use something like transformer and this and that. No, actually there was a research on this and they analyzed that different techniques. And actually in some cases, a small stack of dense layers that such as we saw before with bigrams could actually be a perfectly valid solution. And the analysis that I mentioned before on various text classification, be careful, this is only for classification, techniques across different type of context of text datasets, so big, small, limited vocabulary or not. So this analysis show that there are two important criteria on which method to use. And this is the number of samples that you have, so how many samples you actually have to train your model, and the length of each sample. So what is the average sample length of your sequence? So here's the rule of thumb. If you get this ratio of number of samples for your dataset of number of samples divided by the mean sample length, and it's a number larger than 1,500, then you should probably use a sequence model, like the transformer, for example, or the recurrent networks. If it's less than 1,500, then maybe you should go for a bug of bigrams approach, like the one we did here. But actually, this rule of thumb also applies in our example. You can see that the ratio is less than 1,500. So that's why the bug of bigrams actually performed better. So the sequence models are actually the transformer or RNS better if we have lots of training data, and or if we have samples that are relatively short. Now, all this that I explained before was regarding the classification only. Let's see what we can do beyond the classification task. So here we go for the sequence-to-sequence learning, which is a bit more complicated, so try to bear with me. Sequence-to-sequence application. First of all, what would be some applications? Machine translation, text summarization, question answering. So we ask a chatbot equation or just chatbots, or text generalization. We have a prompt and we want it to the model to produce a paragraph on some topic. So here is what is a general template for this. First of all, the whole idea for all of them is that we just predict the next word. It's just the same thing for all of them. We predict the next word until we arrive to the end. And this is a general template. We have the encoder. one we saw before that turns the source sequence, for example, in translation, it will be the original, the English, in the case that we saw, turns this source sequence into an intermediate representation. And then we have the decoder. So what the decoder does? The decoder is trained to predict the next token I in a target sequence by looking at two things. One is the encoded sequence of the source, and one is the previous tokens from 0 to I-1 of the target. So during, and of course here it's of the actual target. During inference, when we don't have access to the target, then it does the same thing, but it has access to only what the model predicted. And it starts with a seed, let's say the word start, and then we end when it outputs something like end. So this will be the end. We don't expect 600, it will be just this. So this is more or less how it works. So we have the training phase, we get the input and we pass it through the encoder. So this is a source, we get a representation, and we keep the same representation for all the steps of the decoder. And then we feed the word, the start word, for example, and then the word K. And we, first of all, we feed the start and we expect this, given this representation, to produce the word K. Then we feed start K and we expect it to produce tiempo, etc. So this is how it works in the training. In the inference, we just feed the words, they start this token, and we get the output. And then we concatenate the output here, and we get the next until we get the end. Now let's see how this can be implemented. A machine translation example. So let's see how we can actually get Spanish and English words, sentences, and see if we can translate from one to the other. So here we have a specific dataset. You can find how to download this in the notebooks from the original repository in GitHub. And we just have the one pair per line, and it's separated by tabs. So we have the English and the Spanish, and we have the Spanish sentences. We have to add the start and the end before and after, so that we can use them as correct target. And then we just have the text pairs where we have the English and the Spanish. Now, let's see what this would look like. So here we have the English sentence. They were all dressed in uniforms. And here we have what is the new Spanish. So we start with start. Todos vestían uniforme. And we have the end in order to know that it is completed. And let's produce now, let's break it to train, validation, and test. So again, nothing new here. And let's vectorize it. So we will make a small change. So normally you remove the brackets, but now we want the start and the end brackets, so we will keep them. So we have made this change, and we have also made it the change to get the Spanish, the question mark, the upside down. So other than that, nothing new. We just apply what we saw before. So text vectorization, the output will be the integer, and we just implement this for the both the train, validation, etc. Now, one thing that is different here is that we have the source vectorization and the target vectorization. So the idea here is that the target will have one more output here. So we have the sequence length +1 because we want it to be shifted by 1 when we feed. So we will feed the first token, and the target will don't have this. Then we will feed the first 2, and the target will have the first, the 3, and the target will have the 2. So this is how this will work. So let's run this one. And preparing the dataset. So now let's actually prepare the dataset. And the idea is that, again, we will have it to return the dataset, to return the inputs and the target. And for the inputs, we will have a dictionary. Remember, we have 2 inputs. We have the source and part of the target. And the part, yeah, the target. I mean, the Spanish sentence. And the target will be this shifted by 1 step. And this is how we can implement this. So we have the this format datasets function that will take the English and the Spanish. And this will return two things again. So it will return a dictionary with the English part to be the English sentence, and the Spanish part will be the Spanish sentence up to the penultimate sentence token. And then we have the Spanish, which is the target, which is from the second one until the end. So this will not include the word start. And of course, this will not include the token end. And here, let's say, this is how we make the dataset. So nothing important here. We just take this, we make a list from tensor to slices, we batch them, and we map this format dataset. So this is all we can do. And we create the train and the validation. We will not have test, I guess, here. So let's see what this looks like. So here we have, for example, the inputs English to be 64 by 20. So why 20? Because this is the maximum length for the sequences that we defined. It's very short sentences, actually. And the other part of the inputs, the Spanish part, will be 64 by 20, because it includes the start token, and this includes the end token, but not the start. So let's continue to see how we can use first RNN, and then we will see the same thing with transformer. So let's start with the RNN, which was actually quite dominant as a paradigm for these tasks between 2015 and 2017. And Google Translate actually used this. Circa 2017 was a big RNN, I think 7 blocks or something like this. So one detail, so this is the naive way to turn the sequence to sequence. We will not do this. We have the inputs to be whatever is the sequence length, and we have the embedding layer, which takes these inputs and the vocabulary size, and we define what is the output of the embedding. So nothing strange here. And we have the LSTM. So what's the comment here? Okay, I cannot see, I guess. Okay, no. Okay, so we just have the output of the LSTM, and then we pass this. So all this, because we get, so return sequences actually returns the embedding for each word. And then we take this, which will be 20 in this case, and we feed them to the dense layer. So here the idea is that it could work, but it has some not very pleasant features. So there are two major issues with this approach. Is that the target sequence, first of all, has to be the same length as the source sequence, which is not always the case. So we have sentences that are, I mean, it doesn't have to be the same thing. Also, the model only looks the token from 0 to n in the source to predict the token n in the target, which is not very good, because if you have a sentence that says something, it doesn't mean that the same information that is at the beginning of the sentence in one language will be what you need for another language. Especially, for example, in Japanese, if you are familiar, it's totally different. I mean, sometimes you need to listen to the whole sentence in English, for example, to start the translation in Japanese, because the information is in different places. So this wouldn't actually work. The proper way to do this is what we discussed more or less before, is to encode the whole sequence as a vector or a set of vectors, and then feed this and also feed the elements from 0 to n in order to produce the next character. So let's see how we can implement this. We will use GRU, but you can use LSTM if you want. So here we have, first of all, the source. So remember, we have to encode the source in order to feed it later with the first tokens to the decoder. So the source will be just some input. We have the integers here, to 20 integers. And then we have the embedding layer that will take this and will produce the embeddings for each word. And then we take this and we pass them through a bidirectional GRU in this case. So let's build this one. And then this is a model. So the past target, which is the first thing that we feed to the model. We have again an input, and we have the embedding space, the embedding layer applied on this past target. And then we return the sequences here. So this will be first of all, we have this, the output of the embedding. And then we have the GRU, this layer, which will have this latent dim and will return the sequences, applied this decoder GRU on X. And this is the important part, that we have the initial state. So here, the initial state will be the encoder, the encoded source, what we used before. So it will start from this. And then we just take this output of the decoder, of the GRU, and we pass it through a dropout and a dense, which will be of vocab size. So the idea here is that we have, I don't know how many words in the vocabulary, let's say, it doesn't matter what we defined, let's say 10,000. And for each one of the words, we have softmax, so we get the one, I mean, we pick somehow which we will keep. And this is what we want. And for the model, again, remember, we have two inputs and one output. The output, of course, the target, of course, will be the target next step, which is this one. And the input will be the source and the past target. So this is more or less the architecture with the two inputs and the one output, which is the next step. Now, let's see how this would. So actually, the training is nothing new. Here we use accuracy. It's not very good because accuracy means did we find the exact word that should be produced or not. Usually you use other kind of metrics like the blue score. So nevertheless, we use accuracy and we get something like 63.4%. So in 63.4% of the cases, the predicted word was correct. Now, let's see some examples of what is translated using this. So we have the, okay, it produces. So we just prepare the data, the maximum decoded sentence, and then we have this in order to decode the sequence. Nothing, I mean, it's just code that will take the prompt word, the start, and it will call the target vectorization. Then we have this model that we defined and we call predict on this, given these two inputs. So the tokenized input sentence and the tokenized target sentence. And then we just take the maximum, the argument with the maximum score, because we have softmax. And then we just take the word based on this index, so nothing new here. And then in the end, we have this end token. And this is what it produces. So let's see some of them. For example, I'm nothing but a poor peasant. No soy nada más que una. Of course, it doesn't know this word. He says the shift alpha. Okay, it's not perfect, but I mean, it tries. I forgot to buy the textbook. Me olvidó de leer el libro. It's not perfect. It's not, I mean, not bad, not perfect. It works. Somehow it works. And it's actually quite interesting because this was quite simple, simple model, and we didn't have anything. I mean, we didn't use any pre-trained, anything too complicated. We got something decent, I guess. Now, what can we do in order to improve this model, which is the baseline for the translation? First of all, we can have a deeper stack of recurrent networks, both for the encoder part and the decoder part. And we can have also replaced the GRU with an LSTM. And of course, there are many things that we can do. But there are some limitations. First of all, we have the source sequence representation, which must be held in the encoder state vectors, which is increases the size and the complexity as we increase the words, the length of the sentences. And the other bad thing is that the RNNs progressively forget the past, which is a problem because we cannot have really long sequences treated with RNNs. And for this, we have the transformer, which is actually quite good, as you can have probably already seen with long sequences. So let's see how we can take this same task and use a transformer for a sequence-to-sequence learning. There are some tricks here that we have to implement. So first of all, neural tension, the sequence considerably, these can treat sequences that are considerably longer and more complex than the RNN, that the ones that the RNN can handle. And we have the encoder, in this case, that reads the source sequence and produces the encoded representation of it, so nothing new here. But unlike the RNNs, the encoder of transformer, the RNN encoder, the transformer encoder keeps the encoded representation in a sequence format. And it's a sequence of context-aware embedding vectors. So this is the important difference, that we have the context awareness. And regarding the decoder, we have, like the RNN decoder, it uses the first 0 to n tokens in order to produce the n+1. But it uses neural attention to identify which tokens of the encoded source sentence are most closely related to the targets. So let's see how this works. So this is both the encoder and the decoder part. This is what we saw before. Again, we have the input, the 3 input sequences, the multi-head attention, how many heads we have, and then we apply a residual, layer, norm, to dense, again residual, and layer normalization. So this will be the input here. Let's see now the new thing, the decoder. We have the input. Again, we pass it through a multi-head attention, residual, layer normalization, so similar. And then here we have another multi-head attention that takes the 2 inputs, takes this input and also the output of the layer. It passes through this so that it fuses the information, and then we have here the residual connection, layer normalization, and this is more or less what we had before. So another set of dense for projection, but the addition here, the residual, and we have the normalization. And this will be the offset, the target, the output of the decoder. Now, here is the code for, so I kept it here so that you can see both. And this is how we have the transformer decoder. We have already the class for the encoder. Let's see here. So we have the embedding dimension, the dense dimension, and the number of heads, more or less similar to the other one. We assign them. And here we have the first multi-head attention. So this is the attention 1. And then we have the second one. Remember, this is the first, and this will be the second. And we also have the dense projection, similar as the other case, where we have the 2 dense layers. And now we have 3 layer normalization. Again, it's 1, 2, 3. And let's go to the call. Yeah, we will explain this thing. And this is the trick that we need. So let's go to the call function. So, okay, actually, let's first explain this. So the idea is that we want we feed the whole thing, the whole target to this layer, but we don't want this layer to have access to the whole thing. We want it to have access only from 0 to n, right? In order to predict the n+1. And this is why we use this causal attention mask. The idea with the causal attention mask is that it will zero out from n+1 to the end so that the layer doesn't have access to this information. So what we want to do is to take if you remember this matrix that we had before, and zero out the upper part of the matrix so that it doesn't have access to this information. So this is how we make it. We have the inputs, and then we get what is a bud size, what is the sequence length, and we create the I and J based on these numbers. So sequence length, and then what we do is that we generate a matrix of shape, sequence length, with the first, with ones in one half and 0 at the other half, in order to have access only to the first half. So we create the mask, and then we reshape it to be this thing, and then we concatenate these 2 things. We have here, what we do is that we concatenate the ones and the zeros, more or less. So this will be the causality-based attention. So in order, again, to limit the information that this decoder has access to, only from 0 to n. So we create this causal mask, first of all, and we get the minimum between the padding mask and the causal mask. So if one of them has 0, it will be 0, the actual mask that we are going to use. And then we have actually what is going on. So we have the first attention layer, where we have these inputs. Again, here it will be 3 times the target, 0 to n. And we use this causal mask because, again, we don't want it to have access to n plus 1, etc. Then we apply the residual and the layer normalization. And this is the second one. This is the one that has the two different inputs. So we have the attention output, 1, which is the output. I mean, it's this output here. And then we also want the encoded one. So let's go back. We are here. So we want this, and then we want the value to be the encoder output. And for key, again, we want the same as the query. And here we use the padding mask. We don't use the causal mask as before. And then we apply just the normalization on the residual, the dense projection, and again, normalization and the residual. So this is more or less, again, what we implemented here. What we saw here is the implementation in code. Let's continue and put it all together in order to see what will be the result here, and if it will be better than the RNN that we used before. So the positional embedding, this is exactly the one that we had before. I just run it again. Nothing new here. The positional embedding that we saw before, that just adds in the end the tokens embedding and the positions embedding. Let's move to the end-to-end transformer. So this is the whole thing. We define the dimensionality here, nothing new, how many heads. And we have the encoder inputs to be just the integers with the English. Okay, so this will be the English part. And then we have the positional embedding, which will return the embeddings of this. So we apply it on the encoder inputs, and then we pass this X to the transformer encoder. So this part, similar to what we saw there at the classification. Now we have the decoder. So for the decoder, again, we have the same thing as here. So just the decoder inputs, we have the positional embedding, and then we have the transformer decoder that takes, okay, what are these numbers? But it takes both the X, this X, so the 0 to n of the target, and the encoder outputs. Okay, what we had before, so this one. And then we just take whatever is the output, we apply dropout, and then a dense layer with softmax, exactly as we saw before. So it will output, and we will keep the argmax, and this will be the next token. And here is what it would look like if we would train it. So again, just the test accuracy now, because it takes a long time to train. And the result is 65.4, which is actually a bit better than before, quite better than before. And this is the same code as before in order to translate some sentences. And here we can see the actual translations with what we built. So you're my friend, eres mi amigo, okay. We discovered radium. Yeah, of course it doesn't know, not even the word. Who discovered? Yeah, it doesn't know the word discovered in the radium, of course. So is actually, yeah, here it's important that it uses L. So you can see this kind of bias, for example, for gender in this case, in languages that there is this difference. Tom is usually at home. So you can see that, again, not perfect, not bad. I mean, something quite okay for given what we have access to. Now let's summarize everything and close it because it's time. So two kinds of NLP models. We saw the bag of words, which is just sets of words or n-grams, bigram, like we saw before, and we just have dense layers. Of course, we can have some additional stuff, but this is the main idea. We have dense layers with something else. Or we can have the sequence models, which is takes into account the word order, which can be RNN networks, layers, or 1D convolution, or transformer with the positional thing that we saw before. So for the text classification, there is this rule of thumb, which is the number of samples divided by the mean number of words per sample. And this can help you determine which of these to use. Of course, you can try the other, but this is more or less, of course, if the n-gram, the dense works quite similar, it's much faster, so go for the dense one. Sequence-to-sequence learning is a generic and powerful learning framework that can be applied to solve many, not only NLP problems, but many more. So including machine translation, that, like we saw before, we have the encoder, which processes the source sequence, again, the decoder that tries to predict the future token, given the previous ones. And of course, the source sequence. Neural attention is the mechanism that we saw, a way to create a context-aware word representation, and it's the basis for the transformer architecture. And the actual transformer architecture, which includes the encoder and the decoder, that yields excellent results actually in the sequence-to-sequence tasks. And the transformer encoder can also be used by itself if we have some task like the text classification or any sort of single input natural language processing task. So that would be more or less. Thank you very much.